Okay. So today we would start with applications of Biot-Savart law. Some of them you already know, okay, some of which you already know, but not all of them. So we would be discussing a lot more than what you know. So first one is magnetic field due to a straight conductor. I had started this topic last time, but because of time crunch, I couldn't move any further. Okay. Now this is a straight conductor carrying current I, and it is of finite length. Is it okay? So we are generalizing it for finite conductors, and by putting some values we would be taking it to infinite, basically very long conductor. So let's say we have a point here P at a distance A. This is the point where you want to calculate the magnetic field due to the wire. Is it okay? So now let's consider a small element dy. I drop a perpendicular this, so the distance is y from the foot of perpendicular. Is it okay? Okay. So we take a small element dy at a distance y from foot of perpendicular. ठीक? I am joining these 2 points. Let this angle be theta and let this be d theta. Is it okay? Okay, let this angle be theta and the small portion be d theta. So you already know that actually in this triangle I can say y is a tan theta, right? And dy would be how much? A secant square theta d theta. We can actually prove this also. Okay, we can actually prove this also. We can find the length of hypotenuse, and we can take the length of this find the length of this small portion, which is what? A small arc of this angle d theta, and then we can find this, the value of dy. So we can find this as well, but you need not find that by this means. By geometrical diagrams we have calculus for us. Okay. So the magnetic field at this point dB would be what? Mu naught by 4 pi I dl sin theta by r square, right? So what's happening now? This is the r in which we were interested, and this is the direction of current. So we should be taking this angle. Don't you think? We should be taking this angle. Okay. So let's call this angle. This angle is actually what? 90 minus theta. We can call it alpha. So I should be actually using this angle. Okay. Just a second. So I should be actually taking this angle. So this is mu naught by 4 pi I dl is dy actually. We are calculating the field due to this small element. So this is a secant square theta d theta into cos theta by r square. Okay. Okay. Where r can again be written from this triangle, r can again be written like this. A by r is what? Cos theta. In this triangle a by r is cos theta. So r is a secant theta. Okay. So I should be replacing r with a square secant square theta. So secant square cancel. You get a very simple expression, mu naught I upon 4 pi a cos theta d theta. This is due to this small element, right? Okay. This is due to this small element dB, the field due to this small element. Now we want to calculate the field due to whole of this wire. Okay. So what I would be doing, we are interested, we have only one variable, that is theta. So I would be interested in the angle which the corners subtend at this point. So let's join, I would pick blue for this one. Let's join these 2 points. Let this angle be what? Alpha, and it is in which sense? Anti-clockwise sense. Okay. Let's join this angle. This is beta, but this is in clockwise sense. Okay. This is in clockwise sense. So magnetic field would be mu naught I upon 4 pi a integral cos alpha d cos theta d theta to from minus beta to plus alpha. You can take from minus alpha to plus beta as well. See, I am right now interested only in the magnitude. We have another law for direction as well, right? Okay. So you can take whatever you want to take as the upper limit and the other one as the lower limit, but just take care of the signs. One angle would have positive sign, other angle would have negative signs, definitely. Okay. So this would be mu naught I upon 4 pi a. You already know this thing would be sin theta, and when I replace the values, it becomes sin alpha plus sin beta. Okay. So this is the magnitude. Okay. This is the magnitude. If you are taking, while we were doing electrostatics, we were taking the angles formed at these corners. Okay. We were taking the angles formed at these corners. So if you are taking this angle as phi 1, this as phi 2, or this as phi 1, this as phi 2, we are taking lower angle as the upper limit. Okay. So if you are taking these corner angles, then this expression would modify to this one, 4 pi a cos phi 2 plus cos phi 1. The angles would always be added. Okay. The cos values or the sin values will always be added. Okay. And the direction is given by what? Right hand thumb rule, right? So for this element, let's check. For this small element here, dy, it is dy here, this is r, the angle is this. This was actually 90 minus theta, but still we don't need that. For cross product, the expression was ideal cross r on the numerator side, which we wanted to calculate. So for cross product, how do we calculate the values? We always go as we read. We place our fingers along ideal and then we rotate it along towards r. So this would be inward. Okay. For this small element, the field here is inward. For this small element, the field would again be inwards. For another element, it would be inwards. So the net field would be inwards, and we modify our right hand thumb rule. We say hold the current in the direction of your thumb, okay, or rather point the thumb in the direction of your current, and curl the fingers. So magnetic field lines would be going like this. You already know this. Magnetic field lines would be going like this. Okay, so at this point field would be inward. At this point field would be outward. So here we were interested in magnitude. Directions are given by this. Is it okay? By right hand thumb rule. You had been studying this since 11th, right? So I need not elaborate on this. In fact, in 10th also you studied this, right? So is it okay? Okay. Can we continue? So now let's have some extensions to this. The first extension would be infinite wire or long wire. Okay. Our wire was like this. The angles were, here it was phi 2, here it was phi 1. for very long wire, the angles would be, as the wire increases in size, the angles reduce, and for very long wire, the angles would be 0, 90, 0. We are taking the corner angles. If you want to take these central angles, they would become 90, right? So let's stick to this cos thing. Why? Because in electrostatics also we studied cos wala factor, right? In electrostatics also we studied cos wala factor. We at that point of time we calculated the field in x direction and y direction, and for symmetrical arrangement the field in y direction was 0. Okay, in the upward or downward direction they were cancelling each other. So it was cos thing there, which was useful. So let's stick to that only. So phi 1 is equal to phi 2 is 0, right? And B would be how much? Mu naught I upon 4 pi A. Cos 0 plus cos 0 is 1 plus 1, 2. Okay, this you already know, but this was calculated using what? Ampere's law. I guess that it's done. I'll erase this one. This is finite wire. Sorry. Mistake. I'm sorry. Semi-infinite wire. This kind of wire. One corner is known, the other corner is at infinity. Here is the point. Okay, this is A. This angle is alpha and beta is 0, something like this. Is it okay? One corner is known. So the angle alpha may be 90, it may be more than 90, it may be less than 90. We can have many cases. We can have this kind of case, in which angle alpha would be 0. We can have this kind of case in which angle alpha would be more than 90, right? Okay, and beta would be 0 in all these cases. Okay, so in all these cases, what happens? B would be mu naught I upon 4 pi A cos alpha plus cos 90. So this is mu naught I upon 4 pi A 1 plus cos alpha. So sorry, cos 0. Okay, 1 plus cos alpha. So what happens when alpha is negative? What happens when alpha is negative? The values, they decrease. It's okay. So we can have all the possible cases here. Okay. Now, one more thing. What if the point P, can I erase this portion? What if the point P is located along wire? If point P is located along wire, current is flowing like this. Okay. What in this case? In this case, actually, what happens? R would become parallel to ideal. So B would be 0. Okay. B is 0 if P is along wire. Important point. Another point, if the reference point, if the point where you want to calculate the field is on the wire itself, okay, the wire is thin, okay, the wire is totally thin. For this point also we take B as 0. This is, you know, you can say convention. On the wire itself, you cannot calculate the field on the wire itself. Just near to the wire, the field would be very large, but on the wire itself, the field is taken as 0. Is it okay? So B is 0 if Q lies on thin wire. Okay, what happens to thick wire we will see in some time. Okay, now I have a question for you. Let's first solve the let's first go ahead with the circular loop actually, then we'll do some questions on this. Can I erase this one? This is magnetic field due to a circular loop, obviously current carrying circular loop, it should carry current, otherwise no magnetic field. Okay, at any axial point. Okay, and we would study some special cases of this. So this is the current carrying loop. Change the marker. Let's say the point P is here and this is the current carrying loop. So at this point the current is going in, at this point the current is coming out, right? Okay. Now consider, I'll just mark the element here first. This is dl vector and the current is coming out. At this point the current is coming out. Okay, this is placed sideways, right? So consider this small element dl. Now for this element this is r vector. The angle here would be theta. The angle here would be theta. Is it okay? So the magnetic field due to this small element would be how much? dB is equal to what? Mu naught upon 4 pi I dl sine how much? By the distance is r square. So if the radius is capital R and this distance is a, we can take r as under root a square plus r square, right? But what about the angle? See, this element is coming out and r vector is like this. So can you see that they are actually perpendicular? Any line coming out of the plane is actually perpendicular to all the possible lines in the plane. Is it okay? Any line perpendicular to this plane is perpendicular to any possible line, any possible figure drawn on this plane, you know, circle, square, anything which can be drawn, the line is perpendicular to all of them, right? So the angle would be 90 degree, mu naught upon 4 pi I dl upon a square plus r square, right? Now let's check the direction. Okay, let's check the direction for this small element d. You know, you remember the law, keep your thumb along the current and curl your fingers, right? So for this element the field would be like this, perpendicular to r and in this direction. Is it okay? You can use right hand thumb rule as well in the other manner, like dl is in the outward direction, r is like this, so dl cross r would be again in this direction. So either you can place your thumb along I and curl your fingers to get what magnetic field lines would this element produce, or you can use ideal cross r thing. Is it okay? Now this element has current going inward, so for it the field would be exactly opposite, that is like this. Okay, so if we have dl element down here and if we have dl element up there, the two would produce fields like this one dB1 and this is dB2, okay, dB1, and this is also equal to dB2 because the two elements are equal, right. But since their direction is not equal, we cannot add them directly. Is it okay? We cannot add them directly. We would have to take components, their directions are different. So this element here would have component dB1x and this component dB1y, this component dB2x and this component dB2y, right. I'll erase R from here. Okay. Now since the two magnetic fields are equal, their components would be equal again. So these two would cancel. We are interested only in dB1 and dB2 y components. Sorry, this is y, this is x. I misplaced the symbols. Okay, I misplaced the symbols. But now the y components cancel, but the x components they add up, right? Okay. Let's find what are the x components. Now this angle is 90. Okay. Total angle is 90 degree. So this would be 90 minus theta and the remaining angle would be theta. I'll explain it again. Something like this. This was theta. Okay, this was r vector. This is dB1. This is 90 minus theta. Why? Because r vector and dB vector should be perpendicular to each other. Cross product की property होती है, right? This angle would be how much? Theta. So dB makes an angle of theta with vertical direction, right? The horizontal component would be sine component and the vertical would be cos 1. Is it okay? So field due to two dl elements diametrically opposite, dB is what? dB1 sin theta plus dB2 sin theta, which you already know क्या होगा. So mu naught I dl, this would be twice of upon 4 pi a square plus r square. For sin theta in this triangle we can take r upon the hypotenuse. It is r upon the hypotenuse. Okay, the triangle is this. This is the point P. This is the angle theta. This is r, the radius of the ring a. This is small r. Okay, the distance, right? Okay, out of this only dl is the variable. All of them are constant, right? So dB can be, you can combine it. So I'll directly integrate it. This is 2. The magnetic field would be integral. All the constant things they would come out. 2 pi a square plus r square raised to power 3 by 2 integral dl. Okay. Okay. This was the field for two elements. Okay. This was the field for two elements. Now think about it. If I integrate this for first half, the second half is automatically considered, right? Because every time you consider dl, you have to consider this dl as well, so that the opposite, the y components, they cancel each other, right? The perpendicular components cancel each other. So every time you consider this, you consider this automatically. This is considered in this. So if I consider only the half ring, other half would be automatically considered. Okay, one way of thinking is this. Otherwise you can think of like this. Two components have this much field. One component would have field how much? Mu naught by 4 pi. Instead of 2 pi, I would be writing mu naught by 4 pi. Rest of the expression is same. And you can integrate it from 0 to 2 pi r for whole of the length. But right now it includes two elements. So I would be integrating it from 0 to pi r. Okay. Other half is already considered. 0 to pi r. So you would get what? Mu naught I r upon 2 pi a square plus r square 3 by 2 into pi r. Pi cancels, and this is mu naught I r square upon 2 a square plus r square 3 by 2. Okay. This has actually gone into some angle, the text. So okay, I'll give you one more minute actually. So I guess I should be moving ahead. Okay. So what if the coil or the loop has n turns? For n turns, B would be how much? Mu naught n I upon 2 r square a square plus r square raised to power 3 by 2. Okay. Now, you obviously know that we would have some extensions to this, some special cases. Now, if we calculate the value for which B would be maximum, the distance for which B would be maximum, A comes out to be 0. B would be maximum when A is 0. You already know it, right? So we have a special case at center, which means A is 0. At center, A is 0. So B becomes mu naught n I r square by r cube हो जाएगा ये by 2r. Okay, I am not writing everything. ठीक है. Now for an arc, let's say this is an arc which makes an angle alpha at the center. Okay. So you already know that for 2 pi angle the field is this. Okay. Okay. For 2 pi angle field is mu naught Ni by 2r. Obviously for one angle it would be this divided by 2 pi. For alpha angle B is mu naught Ni upon 2r into alpha by 2 pi. Is it okay? For one angle it would be this whole thing into 1 by 2 pi. For alpha angle it would be this thing. Is it okay? So for any segment, for 90-degree angle the field would become 1/4. For 180-degree angle, which is semicircle, the field would become half, and you already know it, how to proceed with this. Okay. So now let's start with some questions. Okay, let's have some questions on this. Shall I erase? At least that part I can erase. Now the question is, the first one is easier. The x-axis, y-axis and the z is in the outward direction. Right? So what happens? Current comes in. At this point of time, So we have three segments A, B, C, D, and this D, E. This is extended till infinity. So D is a line parallel to Z axis. Okay, you need to find the field at origin. The current is I. This distance is A. This distance is 2A. Okay, you need to find the field due to three segments. What is the B for uniform circular ring at center? Somebody has asked. I just explained it, right? Mu naught I by 2R. Mu naught I by 2R is at its center. For n turns, it is mu naught Ni by 2R. Okay. So the total field would be what? A sum, vector sum of fields due to segments AB, CD, and DE. Why? For this portion, the O point lies along the line. So the field due to this is 0. This BC portion lies along the line. The point O lies along the line BC. Okay. The point O lies along the line BC. So this is again 0. So you need to include only the two circular portions and ED. Point is this. ED is coming out from this point. O is not lying along the line. Point is here. ED is coming out like this. Okay. So due to AB portion, the field would be, current is traveling like this. The field would be in inward direction, that is minus Z. If you curl it along fingers, you know already that actually the magnetic field due to a ring, the direction at the center can be found using right hand thumb rule. Okay, this, take the current, consider the current along your fingers. This time, okay, the right hand thumb rule is modified slightly in this scenario. You take the current along your fingers and curl your fingers along the current. Thumb gives the direction of magnetic field. So for anti-clockwise current, the direction is outward, and for, sorry, this, not this, for clockwise current it is inward. So this you already know, right? Okay, I just give a recap. For this portion, this is a quarter circle, the direction is inward. So this would be mu naught I upon 8A. Why 8A? 1/4 of that. We just did it for an arc. So I can write it as 2A into pi by 2 upon 2 pi minus k cap. For second portion, it would be how much? Mu naught I upon 2 into 2A pi by 2 upon 2 pi into minus k again. For the second portion also, field is in the inward direction. Now for the third portion, the field would be, current is coming out, the field would be in downward direction. If you could just check, in the downward direction, minus j. So it would be mu naught I upon, this is a semi-infinite wire. It is coming out from this point. Okay. So what is happening actually? It is this kind of scenario. This is O point at just near the corner. O point is just near the corner. One corner is known, the other corner is at infinity. Okay. When I see from the top, it is like this only, right? So one angle would be 90, other angle would be 0. Is it okay? So mu naught I upon 4 pi A cos 0 plus cos 90 into minus j cap. So you can find the values, mu naught I upon 8A plus mu naught I upon 16A, whole thing with a minus k cap, plus mu naught I upon 4 pi A, whole thing with a minus j cap. Okay. Okay. People often get confused. Somebody is asking a question. explain first question again. This is the only question. I didn't ask any other question actually. So I'll explain it again. You know, a wire comes in like this, okay, from large distance. It rotates like this, then straight portion, then again circular, and then it comes out like this, perpendicular, right? So it's like this arrangement, right? Okay. Now for straight portion, first straight portion, somebody is asking. How you took B for what? ED. Okay, somebody is asking for ED. Now, for I'll explain only for ED because somebody has asked for ED only. So, for ED it's like this. The straight portion is coming, starting from this point and going till infinity, right? So it is not infinite, it is semi-infinite. Do you remember that I said semi-infinite means one corner is already known? Okay. Now what is happening? This is the wire and the point is at this situation, at this location. So one angle would be 0 for the infinite end, and the angle for this end would be how much? 90. Okay. Why? If I see from the top, I see this is the origin. Okay. If I see from the top, this is the point O. We have a point O here. The wire is like this, starting from just this point. So the angle would be how much? 90. The perpendicular dropped. The perpendicular dropped joins the wire at corner point only. So this is 90 degree, right? So one angle is 90 degree and the other angle is 0. This is semi-infinite wire with alpha 90 degree. Do you remember we used the term alpha? Okay. Alpha, one angle was alpha, the other angle was 0, so 1 plus cos alpha, that kind of thing. So this is the scenario. Okay. So that's why, and the direction, current is going out, so the direction would be downward. The direction would be downward, right? This is the value. Okay. Most of the time what we do, we actually do mistakes in directions. So please consider direction of each and every one differently. Is it okay? Calculate, find the direction independently. Okay. Don't mix, please. So I would be erasing it. I hope it's clear. At least I can erase the diagram. Let's have the other question. The other question is this. Okay, this is the arrangement. What's happening? There is an arc, okay, and there is a straight wire. Arc and a straight wire. Okay, you have to find the field at O. You have to find the field here. The angle given is how much? 120 degree. So let's see what happens. Solve it. I am giving you, I can spare not a lot of time, but just 1 or 2 minutes. And I expect some answers from online people as well, please. I guess we should start. See, the magnetic field would have two parts. One is due to arc, and the other is due to chord. The other one is due to chord. For arc, the magnetic field is mu naught I upon, if the radius is a, mu naught I upon 2a into 120 by 360, you already know, right? The direction would be, in what direction? The direction would be outward. Current is circulating like this, okay, anti-clockwise. So direction is k cap. For the other one, it is carrying current in the upward direction. The angle is 120 here. You already know that in this triangle, it is an isosceles triangle. This angle and this angle would be how much? 30. Both would be 30 each. ठीक है, दोनों angle 30 30. Okay, so you know the angle alpha and beta, or phi 1 or phi 2, whatever you may call them, are how much? Mu naught I by 4 pi a cos 30 degree. For corners, for corner angles, you take cos, okay, into 2. Other one is also 30, right? The direction would be, current is going like this, direction inward. So minus k cap. Okay, so let's find the value. Mu naught I upon 6a minus mu naught I upon, if you find this would be how much? Root 3 by 2 into 2. So root 3. So mu naught I root 3 upon 4 pi. How much is the value? Actually, it won't be a. How much is the value? The value is perpendicular distance, this. So it is like this. The angle here is 30 degree. A, this is A, and this horizontal portion, this would be A sin theta. Why? Take the smaller triangle. Take the smaller triangle. Okay. So the side in front of 30 would be sine of that, sine of the hypotenuse. So A sin 30 degree, A by 2. So the distance I should be taking as A by 2. So this would be 2 pi A. Okay. Okay, whole of this k cap. ठीक. Shall I start? Shall I start with the next one? Is it okay? I'll erase the diagram so that those who are writing the solution don't get affected. Now, in this arrangement, what is happening? A wire this is angle theta. What is happening? This is a current carrying loop. Is it okay? This is a wire loop actually, a wire loop. Okay. A straight conductor is joined at one point A and another one at one point B. So basically what? A wire brings in current from point A and another wire takes the current from point B. The current splits obviously into two portions, and you must be knowing that they won't be equal, definitely. Okay. If the wire is uniform, there would be some resistance. Sorry. Okay. So I'll erase this one. The wire loop is uniform. Okay. The wire loop is uniform. Getting my point? So what happens? The upper part would have more resistance and the lower part would have less resistance. See, this thing is not mentioned in the question. This is what we are thinking while solving the question. Which these are the things which we should be solving. We should be thinking actually. Is it okay? Right? While solving. So the wire loop is uniform means what? The lower portion would have less resistance, the upper would have more resistance. Okay? We need to find the magnetic field at O. Obviously, due to this straight portion and this straight portion, the field would be 0. Why? Because O point lies along these lines, okay, along these straight wires, and we already know that magnetic field in these cases is 0. So for I1 and I2, let's see the resistance. Let's say this portion has resistance R1, this has resistance R2. Okay, okay. The resistance R1 upon R2, the ratio is rho L. L would be R theta upon A area. For the second portion, it would be rho. The angle would be how much? 2 pi minus theta. So the length of arc would be R into 2 pi minus theta upon area. So everything cancels. Let's take small r as the radius because it may get confusing since we are using capital R for resistance. Okay, so the resistance is in ratio this, and do you see that actually the two portions are in parallel? Are they in parallel? They are in parallel, right? Okay, so the two portions are in parallel, so the current divides in inverse ratio of resistance. We did this when we were doing current electricity. Do you remember that? We derived this, that since potential difference would be same for both portions, higher resistance would carry lower current. We already know this. Okay, IR is constant. So if R is high, I would be low, definitely inverse relation would exist. So this would be R2 by R1, which is 2 pi minus theta upon theta. Okay, I1 carries current proportional to bigger angle. I1 is the current proportional to bigger angle. I2 is the current proportional to smaller angle, right? So we already know the ratio of currents. Now the magnetic field B1 is how much? For this portion is mu naught I upon 4a into theta by 2 pi, right? यही था I1. Let me take this. यही था. For any arc it was this only, है ना? For any arc this it was this only. Okay. Okay, sorry, 4 गलती से लिख दिया. So now this is how much I1. Let's say this, the value of the ratio is k. Let's take this value as k. Okay, you can think, you can always consider that actually not like this. Let's think. अब total current का how much हिस्सा, out of total current, how much portion is gained by is passing through I1 would be how much? Current I1 would be how much? 2 pi minus theta upon 2 pi into I. Anyone getting this? Anyone getting this? No? I guess we would have to do ratio proportions then first. Do you remember a property called compudendo, in which we used to add the denominator to the numerator? So here it would become, right? So this thing is the whole current I. So I2 by I is how much? Theta by 2 pi, and I2 is how much? Theta by 2 pi, I into theta, theta upon 2 pi. So going by the same logic, I1 would be I into 2 pi minus theta upon 2 pi. है ना? Ratios, you studied this in which class? Which? 6th. So B1 the field due to this one would be mu naught I1 upon 2a into theta upon 2 pi, which is mu naught 2 pi minus theta upon 2 pi into I into theta upon 2 pi. Whole of this, okay, just replacing the values. See, I would not be solving this. Why? Let's check. The field because of this portion, because of the lower portion would be outward k cap, and the field because of the upper portion would be inward. Let's check what is the field because of the upper portion. The field because of upper portion would be mu naught I2 upon 2a 2 pi minus theta upon 2 pi, right? Okay. So you have mu naught I2 was theta upon 2 pi into I upon 2a into 2 pi minus theta upon 2 pi. So, okay, this is minus k cap. The direction is minus k cap. For upper loop it is inward. Don't you think this value and this value are exactly equal and opposite? The two values are exactly opposite to each other. So what happens, the total field, which is actually a vector sum of these two values, is how much? 0 vector, right? It's a vector. So 0 vector, okay? Okay, so I didn't take any value, I didn't choose any value of theta. If I had chosen, I have taken 180 degree, then you by default would have said कि अच्छा नहीं ये तो equal parts हैं, so the field would cancel. The field would cancel whatever may be the case. I reduce the angle, more current would flow through the lower portion, less through the upper, the field is still 0, equal and opposite, right? I increase the angle, again lesser current, the current reduces through the lower portion and increases through the upper portion, again total field is 0, right? And this thing is not valid only for these kind of arrangements. You have a square, you connect this. Still, if the wire is uniform, what happens? Net field at center is 0, because the current distributes itself in such a manner that, okay, everything cancels out. The lower portion would have 3 times the current as compared to the upper portion, okay. So everything, even in a square, rectangle, whatever type of closed figure you take, field would be 0, right, at the center. The only condition is the wire should be uniform, right. So I'll erase this one. Can I erase all of this? Okay. Now let's have one more question and we'll move on to the next concept, right. So the question here is, we have a strip. What does this mean? That it is extended till infinity. Sorry, till infinity. This is here also till minus infinity. The strip has width W, okay, and we have a point P at a distance A, okay. We have a strip instead of a wire. Now a strip of current is flowing. Our strip has some current I, okay. Instead of wire, a strip is carrying current, okay. The strip has width W and the location of point P is A distance from the corner, right. ठीक. So what happens, you need to find the field at P because of this strip. How to approach this? This is not a wire, so you cannot go ahead with the direct formula. What? V naught I क्या? हाँ वो नहीं apply कर सकते. What to do? See, actually, can we consider the strip to be made up of so many thin wires? So let's take a thin wire. Okay, let's take a thin wire. Let's say the distance of this wire is x and the thickness is dx. Okay, the wire, the current I is spread over w thickness. Okay, okay. So current per unit width we can calculate. Okay, so consider a strip of thickness dx at x distance from P. Okay, so now अब क्या होगा, current per unit width. Okay, that is current through a very small portion. How much it would be? Let's call it lambda. It would be I by W. We are assuming that current is uniformly spread over the width. Okay, okay. So current through dx width is how much? Di is how much? Lambda into dx. Okay, okay. Can you think that actually the current per unit width for whole width and for small portion would be the same values, because we assume the current is uniform, right? So this gives us di as I by W into dx. Is it okay? Field because of this strip, field due to strip, thin strip. Okay, here also it was thin. Now field due to thin strip would be how much? TB is equal to mu naught. This thin strip can be considered like a long wire. Wire मान सकते हैं हम इसको. Okay, it's like a long wire. So mu naught di upon 4 pi x, sorry 2 pi x. Okay, the two angles alpha and beta would be 0 0 in the cases, in this case. Okay, so the total field B would be integral dB would be integral mu naught upon 2 pi I by W and dx by x. Okay, whole of this is a constant value. If I replace di, then this thing comes out. Whole of this is a constant value. Only dx by x is variable. The minimum value of x is how much? A, and the maximum value is a plus w. So a to a plus w. Take this thing out. This integral dx by x becomes, yes, log to the base e, or which we call ln x. Is it ln x or is it ln x? Actually, it's pronounced in India, we call it ln x. It's called ln x. I guess it's like that. You would have to ask maths sir actually for this, but that's what I heard from students. Okay, so when we put the values, the upper limit is a plus w, the lower limit is a. So ln a plus w minus ln a, we can use the property of log by which they would become numerator denominator. Is it okay? So this thing would become mu naught I upon 2 pi w ln a plus w upon a. This is the final answer. Okay, and it was a part of JE few years back. Okay, it was a part of JE few years back. What happened? Any confusion? Any difficulty? No? So can we start with the next topic? I'll at least erase the figure. Okay, it's done. Okay. Ampere circuital law is the next thing that we would study. Can I erase the rest of it? Okay. Now, Ampere circuital law, you already know what is this law. Please, if you could just do the honors. Anyone? What is Ampere circuital law? It says line integral of magnetic field over a closed loop. Okay, that closed loop is called Amperian loop. Okay, is equal to what? Times the current enclosed, right? So you already know that line integral is nothing but B dot dl closed loop is equal to mu naught into I enclosed. This is the law. Okay. Okay, I am not writing the the word format of it. I am just writing the mathematical format. Right? Somebody is asking. No. Okay. So let's say we have some current going like this, some current going like this, some current like this. Okay. And this is an imaginary loop which surrounds the wires, the current I1, I2, I3. So how do you calculate the line integral? Take a small element dl. Okay, the direction is upon your choice. The direction is upon your choice. So if you take it, if the magnetic field is along the same direction, you would get the dot product as positive. Otherwise you would get it negative, right? Okay. So let's say B at this point is in this direction. So there would be some angle involved. We take care of that angle as well. So we take dot product of B vector and dl vector for these small elements added. Okay. This is how we calculate line integral, and it is equal to I mu naught into I enclosed. Now my point is, which direction of current would you take as positive? Which direction of current would you take as positive? You cannot take any random direction, right? You cannot take any random direction. Is it okay? Not okay? Okay. So which direction do you think? See, if you assumed that the field is in anti-clockwise circulation, you would take upward direction as positive and vice versa. So you take current, the direction of current according to what? According to how you travel through the loop. Is it okay? As you travel through the loop, you find that the field is along anti-clockwise or clockwise, right? Okay, right? So in most of the cases, actually, whatever we do, we directly or indirectly, all the problems, they have by default taken the positive value, okay, without giving any extra words on how to take the direction. So this is how you take the direction, right? As you circulate in the loop, you check what is the direction of magnetic field, and according to that you take the directions. Okay. So in this scenario, we get B dot dl is equal to mu naught into I1 minus I2. Why? Because we take field is circulating in clockwise direction. So upward current is taken as positive. Upward current positive. The field is like this. So upward current is taken as positive and downward as negative. Okay. Now my point here is, in this statement, B is what? Somebody has asked some doubt. Would the field remain? Achha, somebody asked some question for what if we convert the strip into a cylinder? The earlier question, we had a strip. So the student is asking, what if we convert the strip into a cylinder? We would be covering the cylinder as well in Ampere's law, don't worry. Okay. Somebody has asked, would the field remain? Yeah, it's not same hona chahiye. In which scenario are they asking actually? I think it is because of cylinder only, for cylinder only. If the doubt is for cylinder scenario, we would just be covering in a cylinder field due to a cylinder in maybe 15 minutes more. So if you have any other doubt, ask, or I can go ahead. Okay. If you have any doubt related to cylinder, it would just be solved in some time. Okay. So now the point here is B is due to which current? I1, I2, I1 and I2, or all? What do you think? All or I1 plus I2? I1 and I2? All. The field here would be because of this as well. The current I3 plays no role in the right hand side, but it will play a role in the left hand side. Is it okay? Okay, magnetic field will be affected by presence of this current. But the line integral, the value of line integral would still remain same. Only those currents which pass through the loop change the value of line integral, right? So it's like Gauss law. In Gauss law, what you studied, that outside charges would change value of field but not the flux. So here the outside currents would change the value of field but not the line integral. Is it okay? Is it okay? So if we remove I3, the field would change but the value of line integral would still remain same. Is it okay? So we have quite a lot in common here between Gauss law and the Ampere law. Is it okay? Both are used to find field in symmetrical cases. In Gauss law, you have already done that. Actually, what happens? We take some, for a conductor, we take a Gaussian surface such that it is symmetrical, which means charges are equidistant and so on. Here also, we take loop in such a manner that the current, the portions carrying current are equidistant, right? Here also. So exact similarity and exact behavior as well, that B here is due to all three currents, but the line integral will have value only because of I1 and I2 only. So even if we remove I3, B would change, line integral would remain same. Is it okay? Okay. And what if we apply these laws for asymmetrical surfaces? What if the surfaces are irregular, but still in Gauss law the surface is closed, and in this case the loop is closed? Getting my point? In Gauss law we have an irregular surface. Would the law be valid? Would the law be valid? If this is a closed surface, you have some charges here. Would the law be valid? The law would be valid for all possible cases, for regular, irregular, any type of surface, but it should be a closed surface. That's the only condition, right? That's the only condition. Okay? Okay? Only the problem is that in irregular cases we won't be able to calculate electric field with the help of Gauss law. We won't be able to take the benefit of Gauss law. Same thing applies to this. For irregular loops, okay, or asymmetrical arrangement, Ampere circuital law is still valid, it is universal, okay, but the problem would be what? The problem is that we won't be able to take any benefit out of it. We won't be able to calculate field. Is it okay? Is it okay? So we would have to switch back to our old workhorse, which was Biot-Savart law. It is our old workhorse because we can find the field due to a very small element as well. Okay? So if we have good computational tools, we can find field for any kind of situation using Biot-Savart law, but not for this. Okay? The law is still valid. Is it okay? This was one of the question asked in an easier exam, not in JEE, okay, that some irregular loop was given, so it was asked whether the law would be valid and all. 4 options were there, and most of the people thought that the law would not be valid because they were never taught anything beyond the irregular cases, beyond the regular cases. Do you remember that in your NCERT textbooks only the regular cases were considered. That doesn't mean the life ends there. The law ends there. The law is applicable still everywhere. Okay, you can take infinite sized loop, the law would be valid still. Is it okay? So I'll erase this one. Okay. Now you already know how to take the loop. The loop is taken in such a manner that current is equidistant from the points of loop. Is it okay? Okay. So for a wire B due to a wire, we already know long wire. Okay. We already know this. So I am just discussing how to take the loop. So this is the kind of arrangement. Okay. Let's say we want to find the magnetic field at point P. So we the point P is at a distance small r from the wire. So we take a loop such that it passes through P, but its center is on wire. We take the loop in such a manner that its center is on wire, but it passes through P. So it would be a loop of radius r, and actually every point would be equidistant. You know it. So since every point would be equidistant, magnitude of field would be same. We already know that for this kind of arrangement, field would be like this, circulating like this. So field at every point would be what? Tangent to along tangent, okay, overlapping with the ring. So B dot dl in this scenario for closed loop would actually be B dl cos 0. Okay. And since B, the magnitude of B would be same at every point, we can take it out. This would be dl. So dl for the closed loop is adding small elements, adding the length of small elements, which would become B into 2 pi r, and which would become mu naught I. So B is what? Mu naught up I upon 2 pi r. You already know this. Okay. Mu naught I upon 2 pi r. Is it okay? You already know this. Okay. Now check this, that actually we try to take the Amperian loop in such a manner that the angle either becomes 0 or it becomes 90, so that we can take either take B out, okay, or we have to ignore the term. We consider the Amperian loop in such a manner that either we can ignore the term or we can take B out, otherwise it's insolvable, right? So for a long wire, it's already done. I'll erase this one. Now let's have this for a long solenoid. This is a solenoid, okay, tightly wound it should be actually. This is tightly wound. Okay. What we are doing is, we are, for our drawing purpose, we are taking it to be a little, taking the space between the two turns. Okay, it would be tightly wound, no space. So what we do in this case, now because of all the circular turns, if the current is like this, because of all the circular turns, the field would be in this direction. Okay, field would be in this direction. You can check for all the circular turns, either in this direction or in this direction. It's okay. So let's see that. Let's have the current in this direction, right? Okay. Somebody is asking a doubt again. Is this formula valid for? It is valid for infinitely long wire, but it is not valid for finite wires. That's why I introduced the formula for finite wire earlier. Is it okay? Is it okay? It is valid for infinite long wire. We just did the formula, the Ampere's law. We just used it for long wire, infinite wire, but it cannot be used for infinite, for semi-infinite or for finite wires. Why? Because the value of B is not same at all the points, plus additionally the angle between B and DL would not be 0 every time. Is it okay? The value of B and DL would not be 0 every time. Okay, so we need to have the loop in such a manner that either the angle is 0 or it is 90. Okay. Now the tightly wound, it is tightly wound. Okay, and since all parts, the current is circulating like this, all parts have this kind of circulation, the field would be like this. Okay. For an inner portion we take a loop here. You already have done this, so I won't be taking much of the time. We take n, small n, sorry, let the total length be capital N. So we can have n is equal to capital N by L. This is the number of turns per unit length. Let's first find the line integral. Okay. Now the line integral would be due to 4 sides. Okay. This is the line integral associated, the line integral associated with side AB, line integral associated with side BC, CD and DA. Okay. Now let's check what happens for AB. The solenoid carries straight magnetic field. No magnetic field leaks out of this portion. You getting my point? For a tightly wound solenoid, no magnetic field leaks sideways. Only point from which it can come out is at the ends. It goes in from one end and comes out of other end. No point at the middle portion outside will have any magnetic field. Is it okay? The field will not leak at this point, from this point out. So B outside would be 0. So we need not consider this. For BC, some portion is outside, the line integral is 0. Some portion is inside, for which the direction of DL and magnetic field is perpendicular, okay, to each other, 90 degree. Again this goes similarly for AB, for AD, for DA this goes. For CD only we have this kind of circulation in the field. Okay. For CD portion we are traveling along the field, the angle is 0. Okay. If this rectangle has a length L, then the line integral would become BL. Why? Because we take the magnetic field to be same at every point. The magnetic field is straight, okay, uniform, because it is not leaking at all, right? Magnetic field would be uniform, and we can take, since the angle was 0, we can write it as B dl cos 0 for CD, which would become B integral dl, and which would become BL. So this is the left hand side. Let's consider the right hand side. For the right hand side, just think about it. What happens actually? Let's have a sheet of paper. This is a sheet of paper. The current comes from downward, pierces through our loop, then comes from downward, pierces through our loop. This is what happens repeatedly. Okay, it's like when you do embroidery, right? Okay, your that needle comes when you do embroidery on the corners. How do you do it? Your needle comes out from downward, then pierces through the cloth, then comes out, pierces through the cloth. Every time it is like this for the corners. So this would be like this only. Current comes from downward and pierces through the loop every time. So do you know that actually whole of the current is going through this in the inward direction? Okay, it comes from downward direction but enters through the loop in the inward direction, right? So since all the loops in this region are carrying current inward, let's find the total current. RHS would be how much? Mu naught into I enclosed, which is how much? For one wire, the current is I. For one wire, it is this. This is capital N, actually, capital L. For, N was the number of turns per unit length. For L length, number of turns would be NL. So, total number of turns would be NL. So, for NL turns, current would be this much. Now, let us equate. BL is equal to mu naught I NL, L cancels, B is equal to mu naught NI. And this is what you already knew. Let us add something extra to this. Okay, this is what you already knew. Okay, the only thing that I have added is that the current enters every time it enters through the loop, but comes out from downward portion. So not through the loop, right? Comes out not through the loop and enters through the loop. Embroidery patterns. So the only addition is this. Let's add some value to this now. Can I erase this? No, this was a long solenoid. This was a long solenoid. Now this was the point P where the field was mu naught Ni. Let's cut it into two halves. When I cut it into two halves, what happens? The P point becomes a corner point. What would the field be now? At P point, the field was produced by two half portions, and it was originally mu naught Ni. When you remove one half, the field produced by that portion also goes. So the field now becomes mu naught Ni by 2. Okay. Okay. So magnetic field at the corner is always how much? Mu naught Ni by 2. Since every solenoid can be considered as a half of one bigger solenoid, every large solenoid can be considered as one half of a double sized solenoid, right? So for every possible solenoid, this is the field at corners. Okay, this is at inner regions. Okay, anything which is inside, not near the corners but away from the corners. Okay, so somewhere in the middle region, kind of, not exactly the middle point. So this is inner region. Shall we start? Now the question in the next topic, somebody was asking for a cylinder, so let's have the cylinder now. So this is B due to a hollow cylinder. We'll have solid cylinder as well. Okay, this is a hollow cylinder carrying current like this. Okay, so what happens? and it should be long actually. Again, same kind of situation. We cannot apply this to a wire. Why? For a finite wire, the field is not always at 0 or 90-degree angle to the loop. Okay, that's why the issue. So again, it should be a long cylinder. So that field is uniform in every region. Is it okay? Now the current is carried only by the circumference portion, not by the inner portion, and this is the axis. Okay, let's say this is the radius capital R. So we have two regions, one is inner region of a cylinder and one is outer region of a cylinder. Okay, for an inner point, the loop would be like this, symmetrical loop. Okay, let's draw it using blue color to differentiate it from. Okay, this is the loop for inner region. Let's say the distance from axis is r. Okay, so we have a point P at a distance r, given the condition. Where is the duster? Okay, with the condition that r is less than capital R. Okay, for an inner point, what happens is, you take Amperian loop which passes through the point P, but which has center at the axis. It is symmetrical. Since no current passes through it, magnetic field would be 0. The line integral is 0, and obviously L can never be 0 for a loop. So for outer point, for which R is greater than equal to R, let's say we have a point Q here. Okay, this kind of loop is there. Okay, again this distance is small r. We always take small r as the distance. Why? Small r is considered a variable in these cases, all the cases. So for an outside point, small r, the given condition. Okay, now whole of the current is inside the loop. So the right hand portion would always have I enclosed equal to I, but let's find the left hand portion. So it is B dot dl. For whole of the portion, the field would be like this. Current is going up, the field is clockwise. So again, if you take dl as this, obviously magnetic field would be parallel. Dl and magnetic field would be parallel, so angle would be 0. I'll write this as B dl cos 0. And since symmetry is there, all points would have same magnitude of B. So I would bring B out, and this would be dl. Okay, so B into dl for closed loop. Okay, so what we are doing is we are adding length of small elements, which would give me the length of whole of the loop. Okay, so this is 2 pi r, and this is equal to mu naught I. So B is how much? Mu naught I upon 2 pi r. So let's draw the graph as well. Till the portion r is equal to capital R, the field is 0. Okay, till this portion B is 0. Then suddenly at this point, the field becomes maximum. This is B max, which is what? Mu naught I upon 2 pi capital R. As r further, the distance further increases, the field decreases, and it is following a what? Inversely proportional. It is following a rectangular hyperbola kind of curve. right? Okay, let's have this for a solid, long solid cylinder. Okay, just finish this off and we will start with the next thing. Shall we start? Okay, and you know the diagrams are not that dirty, so I would be reusing them. Is it okay? Inner portion is all filled up. So the current is not carried by the rim only. I'll erase this portion. Can I erase this one? Okay, everyone done? So the since inner portion is filled, the current is carried by inner portions as well. Okay. Okay. So current is coming out of whole of the face, not by the rim, not by the rim only. Okay, whole of the face. Every portion is bringing out current. So for this kind of scenario, I would like to define, would like to use a term that is called what? Current density. Okay, I would like to reuse a term called current density. Is valid for n number of circular rings, which I am not getting the question. We are doing a cylinder actually. So yeah, cylinder would not have n number of rings actually. I am not still clear. You know, the blue thing is not a ring actually, it is our Amperian loop. Okay, so if you consider it to be a ring, I am really shocked. This blue thing is an Amperian loop. Is it okay? So if there is any other doubt, please ask. I am a little confused. I mean, like we discussed ring way back at 9, around 9:30. So 1 hour back. So I'm a little confused. Okay, that formula was valid for n number of turns. I'm not sure how you are fitting the ring in there. Okay, in the cylinder. So let's continue. So here this of the matter is carrying current. So I would like to reuse a quantity called current density. Why? Because for this portion, some only inner portion would carry some current, right? Only inner portion carrying current, is considered, right? Somebody is saying how to take direction of what? DL. I just discussed that we can take direction of DL arbitrary. We just need to stick to the direction of current. Okay. Okay. So if magnetic field is circulating in anti-clockwise direction, I take current such that upward direction is positive. Is it okay? I take DL and V in such a manner that these sign differences, they don't crop in. What would happen if I take DL and B opposite in this scenario? B dot DL would give me a negative value. Okay, but ideally the magnetic field should come out to be a positive value, because we already know that if current is upward, the field would circulate in this manner. Is it okay? So we take take the value of the direction of DL according to the situation. That is, if circulation of magnetic field is anti-clockwise, is considered to be anti-clockwise because of the current, we take DL in that direction for positive current and so on. Is it okay? I just discussed it way back when I was starting with Ampere's law. So please go through it, right? Okay. Now J, the current density, this is the current I, would be pi r square. Okay. Now for inner point, only this portion would be carrying current. Let's say we have a point P, so for which the Amperian loop would be, let's not draw this. We have a point P at a distance small r from the axis. So we have this condition that small r would be less than capital R. So for Ampere's law, the I enclosed would be only shown by this blue arrows. Is it okay? I enclosed would be the current that passes through this, okay, only through this loop. So how to find I enclosed? You know the current density. Current density is what? Current per unit area, okay, I by A, okay. So if you find if you know the current density, you can find the current through this portion by multiplying it, by multiplying its area with the current density. So this is J into pi small r square, I by pi r square into pi r square, okay. Okay, you can still use this logic that current density would be same for even for inner region. If I take it to be uniform, current density would be same for inner region as well. Current is flowing uniformly, right? So for inner portion, current enclosed by inner area is also the same. So this is the current enclosed, okay. Now for Amperian loop, again I will explain the direction. Since current is going up, we are taking the direction of magnetic field to be anti-clockwise, okay. So I take dl such that it gives me an acute angle with B, smaller angle with B. Is it okay? Is it okay? So either you have to assume the direction of dl first and take direction of B and I accordingly, or you have to do what? You have to take the direction of current first, then find the direction of magnetic field. Is it okay? And take the direction of dl later on according to these values, okay. कोई एक चीज तो पहले से सेट करनी होगी, right? Okay, so either you set magnetic field first and the current first and adjust dl accordingly, or reverse, right? So in this case we already know the magnetic field is circulating like this, so we take dl in this direction itself, okay, so that the angle is acute. So integral, the loop says this B dot dl is mu naught I enclosed. This is what? B dl cos 0, closed loop. And you know, since all points on the Amperian loop are equidistant, the magnetic field magnitude would be same, okay. Magnitude of magnetic field would be same, right, since all points are equidistant. So we can take B out, this would be this thing, cos 0 is 1 already. So dl is what? Small element here on the loop. So by integrating dl, you are adding the length of all elements, which is circumference. So this thing would become B into 2 pi r, which is actually equal to mu naught I r square by capital R square, okay. B is how much? Mu naught I upon 2 pi capital R square into small r. So for any point inside, this is the field. एक बार और बताऊं. See, the left hand portion is easy, okay. B, the value of magnetic field at every point would be same, the magnitude of only, okay. I am considering the magnitude only. Since for this portion, this element dl would be parallel to the magnetic field. The magnetic field is in anti-clockwise direction, so it would be parallel. Angle would be 0, okay. So this dot product reduces to this, cos 0 is 1, and here B is magnitude of magnetic field. Since all points are equidistant from axis, symmetry exists, we would say that the magnetic field would be same at all points, magnitude only, okay, direction is different. Already we discussed this. Because it is circulation, so direction would be different, tangential at all points. So the magnitude would be same. We can take B out, constant quantities can be brought out of integral. So this is constant, we take it out, we integrate dl. dl is what? A small element, length of small element, okay. So we keep adding dl, what we get? Total length of the loop, which is 2 pi r, okay. And we just calculated the enclosed current to be how much? I small r square upon capital R square, pi cancelled this thing. So the magnetic field is this. Now for B portion, outer point, for which the condition is R is more than equal to capital R. For this, whole of the current flows inside. For this kind of scenario, okay, the point Q, for Q point, whole of the current flows inside. So I enclosed is how much? Total current I, and B dot dl, if we calculate the line integral, again the same thing, that B dl cos 0 hoga, cos 0 is 1. We know that value of B, the magnitude of B is same at every point. This is B dl closed loop integral, which is actually B closed loop integral dl, which is B into 2 pi r, and it is equal to mu naught I. So for outside point it is the same, like a wire, okay, but r is the distance from axis. Is it okay? Okay. So if we draw this graphically, B versus R, can you see that for inner portions magnetic field is proportional to the distance from axis? Magnetic field is proportional to the distance from axis, rest all is a constant. So for this, magnetic field increases linearly, B proportional to R. It reaches a maximum value at what? The surface. When R is equal to capital R, the value reaches maximum. Okay, this is R equal to R, and the maximum value is mu naught I upon 2 pi capital R. Afterwards, it reduces, follows the same rectangular hyperbola graph. Okay? Afterwards, it follows the same rectangular hyperbola graph. Rectangular hyperbola type ही है, asymptotic curve है. So shall we continue? या लिख रहे हैं आप लोग? कुछ लोग लिख रहे हैं अभी भी. So let's continue. Now, this is B due to thin, infinitely wide, long strip. So you getting my point? It is thin, it is infinitely long and infinitely wide. Is it okay? Okay, infinitely long and infinitely wide. So we strip, let's think about it. We have this strip, okay, it is carrying current inward, okay, I current is going inward, and through every point. Here it is extended till infinity. So what is happening? An infinite sheet is entering through the board, right? The width is infinite and the length is also infinite. Okay, okay. So Don't you think that it is a perfect case for our Ampere's law? Everything so infinite kind of. Okay, okay, okay. So this is called a sheet of charge. Strip. We can use a sheet actually. Sheet word. This is a sheet of wire. Sheet of current. Sorry. Is it okay? Okay. So it's like a square carrying current along its surface. Now increase the size of square in every possible dimension. So this was a square. It was carrying current inward. Increase its width. Increase its length. This is what's happening, right? So in this kind of scenario, current is passing through everywhere. Now see, we define a quantity, I current was passing, we define a quantity called current per unit width. You remember this from the earlier question, the strip wala? That strip had finite width but infinite length. Now increase it. Okay, that thing is happening. Okay, so current per unit. Let me erase this one, write somewhere down. Current per unit width. Let's call it lambda. It would be how much? I by the width, but you know the width is infinite. The current is also infinite because every point is carrying current and it's infinite width. So we won't be able to write the value for whole of the strip, but we can write it for small portion, right? We have this small portion dW width. Now this is carrying dI current inward. Okay, okay. And if the sheet is uniform, if current flow is uniform, you would still be able to understand that dI by dW is same for all possible portions. Is it okay? Okay, if the sheet is uniform. If the sheet is uniform, okay. Now to find this, consider, let me draw it with the blue. The Amperian loop is, I'm trying to draw it in blue so that we have some color codes for identification. Consider this Amperian loop, okay, a rectangular Amperian loop. The width is W and the height H, you may call it. The width is W, the height is H. Okay. So let me mark the points A, B, C, D, and the point of interest was this P. P is the point where you wanted to find the field, right? Okay. P is the point where you wanted to find the field. If you want, you can take the distance from the sheet to be x. So if this is x, this has to be x also. We take the loop symmetrically, draw the loop symmetrically, right? Is it okay? Okay, so the width, so the height is 2x, right? Now let's calculate for LHS B dot dl. This is similar kind of arrangement as that in what? In solenoid. So this is what? Again B dot dl for all four parts AB, B dot dl for BC, ठीक है, B dot dl for CD, okay, B dot dl for DA, okay. For BC, the direction of traveling is like this, okay. Let's think about it, what happens. Now this sheet is here, okay. At this point, this, let's say this portion is there, the field produced by this portion would be somewhere like this, right? We have another portion, the field produced by this portion would be like this. So if we take symmetrical portions on both sides, the net field would be like this. okay, and an infinite sheet would have infinite number of symmetrical portions, right? It would have infinite number of symmetrical portions everywhere. From this point, if there is some element here di, there would be some element di on this side as well. The field produced would always be in this scenario equal angles. So it would always give us resultant in which direction? Horizontal direction, parallel to the sheet. It would give us directions parallel to the sheet. See, there is an issue also. I took the loop in this direction while the flow of magnetic field is like this, and in the lower portion it would be like this. So what we would get? We would get a negative answer. Okay, but you know, a positive value and a negative value is immaterial to us. Why? The point here is that actually we already know the direction. Okay, a negative sign or a positive sign, they give us the direction for vectors. So we are interested only in magnitudes. Is it okay? Is it okay? So it is. This is what I was saying when I was giving you the directions, telling you the directions for dl in case of Ampere law. Is it okay? If you take wrong directions, don't worry, you would still get the same magnitude but opposite sign. Okay, so that's why you take, that's why you need to take the direction of dl, the direction of b beforehand. Okay, and take dl such that it makes smaller angle. We have taken from A to B, the dl movement would be like this. We have taken it opposite. Is it okay? Obviously we can anytime change it. We can write it as that, okay, my mood changed, I am no longer going from ABCD, I am going ADCB or DCBA. I can change the direction anytime. Okay, okay, I am interested only in the magnitude thing. So let's go ahead with the same directions and let's remove the negative sign in the last step. So for AB portion, since all points are equidistant, magnetic field would have same magnitude and the angle would be 180 degree. So I will write it as B dl cos 180 degree, closed loop, no, not the closed loop, sorry, I accidentally placed it everywhere. Okay, ठीक है? For BC, dl and magnetic field are perpendicular. Magnetic field is like this. Magnetic field is like this. dl is vertical, right? So goes for a toss. 0. Also for CD, same kind of scenario. Magnetic field is going like this. We are traveling like this, opposite. So angle is 180 degree again. So this is 0. This is B dl cos 180 degree. Again for the fourth one it is 0. Since CD and AB are equidistant from the sheet, magnetic field up there and down here are same. Okay, are totally same. So we can take B outside. This thing would be B. This would be minus B dl. So let's take minus B outside. This is minus B. Okay, and dl would integrate to L. Even in this case, minus B dl would integrate to W width. Okay, dl is the small length of this element. So the total length of AB is how much? W for this also. So can I write minus BW, 2BW, which is mu naught into how much? How much is the current flowing now? We have calculated the left hand side. For the right hand side, only this much portion of current is to be considered, only this much. We already know the current per unit width lambda. For W width, the current would be lambda into W. Is it okay? Okay. Lambda is what? Current by width. So current is lambda into width. Lambda into width. This cancels. B would be how much? Minus mu naught lambda by 2. Okay. Okay. And we ignore the negative sign. Why? Because the magnitude is mu naught lambda by 2. The direction is as indicated. Negative sign generally gives us the direction. So what if we take direction of Ampere loop to be opposite? This happens. A negative sign would come. Okay. Okay. So the magnitude is actually mu naught lambda by 2. Okay. And if you see, this is independent of x. x came nowhere in this expression, nowhere in the derivation also. So which means the field would be uniform. So if this is the sheet, field would be uniform up there, down here. Okay, field would be totally uniform. Okay, even for larger distances. Shall we start? Okay, shall we start? I'll erase all this. Now, what if the sheet is not thin anymore? Okay, see this this came recently for thin sheet. Recently a question came, which I don't remember exactly whether it used this value or it asked you to calculate this value. Is it okay? Whether it used this value or it asked to calculate. So this is not something which is actually way beyond your scope or something. Is it okay? It is still in your syllabus. It still uses Ampere's law. So the next one is thick, infinitely wide, long sheet. So this kind of arrangement, okay, all this is carrying current inward. The width is, let's call it d. The width is d, thick strip hai. Okay. Now in this scenario there would be what? In this scenario there would be an inner point and an outer point, and we can find the magnetic field for both. So let's check. We have this central plane, okay, middle plane. This is the central plane. Okay, plane of symmetry we also may call it. Above this and below this, equal amount of current flows. Now here the current is carried through a cross sectional area. Current is carried through a cross sectional area, right? Getting my point? Okay. Here you won't be defining current per unit width. You would be defining current per unit area, the current density thing, right? Okay. Infinite amount of current and infinite amount of cross sectional area, right? Is it okay? So you define a quantity, current density, you use a quantity, you already know this. Current density, let the current density be J. Okay. So for an outside, let's say there is an outside point at a distance r. There is an outside point at a distance r. Okay. For this, the Amperian loop would be like this. Obviously, the distance here would also be r. Symmetry has to be maintained, right? So r distance above and r distance below. This is the kind of loop. Okay. The current enclosed would be this much. Any current passing through this shaded area will pass through the loop. Is it okay? Any current through this shaded area. Let me just empty the shaded area. Okay, so any current passing through this loop has to any current passing through the loop goes through this shaded area. Is it okay? Let the Amperian loop has length L. The width would be 2r, length L, width 2r. Is it okay? Okay. Okay. Now here the current would go through a rectangle whose length is d. Length is L and width is d. Is it okay? Okay. So the width is d, the length is L. Current only goes through this much area. So I enclosed, I am just first I am calculating for outer area, outer point, okay, for which R is greater than d by 2. Okay, R is greater than d by 2. So for this point, I enclosed would be how much? J into the area of this shaded region, which is what? The length is L, the width is d, JLD. Okay. Now let's find the closed integral. Okay, you already know we have 4 portions. Okay, I'll mark the portions correctly this time. Okay, A, B, C, D, so that you don't get a negative sign this time. Okay. Now from A to B, you already know that current magnetic field will be like this in the upper region, and it will be like this in the lower region. Okay. So from A to B, the dot product would be BL straight away, BL cos 0. For C to D, the dot product would be BL cos 0 again. Okay, BL cos 0. So BL plus BL. For side portions BC and CD, angle is 90 degree. Angle between B and the DL vector is 90 degree. So dot product 0. So 2BL is how much? JLD B, mu naught into I enclosed, which is JLD. So L cancel, B is how much? Mu naught JD by 2. No R in this expression, which means it is independent of distance from central plane. Independent of distance from central plane. Okay. The second would be inner point, okay, for which R is less than equal to d by 2. Okay. So let's try what we can find. Okay. Now this is a point जिसमें हमें interest था. The distance is R. So for this, the Amperian loop would be like this, right? For this, the Amperian loop would be like this: R distance up and R distance down. From central plane, R distance up and R distance down. Let the length be L again. Okay. So again we would consider current through this area only, right? Current through this area only, the shaded region. Okay. So let's find the current. I enclosed would be how much? How much? How much? J into the area, which is L into 2R. 2LR. Is it okay? है ना? Again this closed loop integral. Now this time I won't explain. This is the 4th time maybe, right? Again it will be 2BL. Okay. For side portions, for vertical sides, this would be 0. For horizontal sides, this would add, just like the previous case. So 2BL is J2LR, obviously mu naught into this I enclosed. Okay, mu naught into current enclosed. So L cancel, 2 cancel, B is what? Mu naught J R. Getting my point? This time for inner points it is valid. For inner points it is dependent on R. It is dependent on R. At central plane the magnetic field would be 0, but as you move away the magnetic field increases, and when you exit, when you come out of the sheet, it would become constant. So if we draw it graphically, it would be like this: B versus R, like this, then constant. The point here is R is equal to d by 2. At d by, after d by 2 it is constant, right? Okay. So can I erase this? Now last but not the least, B due to a tightly wound toroid. Now this you already know. After all this difficult stuff, this would feel like heaven. Okay, so my toroid is not exactly going to be a circle. My toroid is not a circle, sorry. Okay, this is not axis. Axis would be this actually. This is the mean radius. Do you know what is mean radius? If I join all the centers of all the loops, you get a mean circle whose radius would be mean of inner radius and outer radius. So this is mean radius. Okay, this is mean radius. Okay, so for this you already know. Now this is again embroidery. You have a circular cloth. Every time current goes in, comes out from sideways. Okay, so all the n turns would take the current in only. Let's say we have n turns. Okay, so small n would be what? N upon 2 pi r. This is the number of turns per unit length. Number of turns per unit length, right? Okay, so by Ampere's law you can consider this, right? Okay, since it is totally closed, the magnetic field outside would be 0. All the magnetic field would circulate in like this inside, not at the mean radius, not at the mean radius, everywhere. It would be like a tube filled of magnetic field. Is it okay? Okay. So for every portion, magnetic field and dl would have same direction. Magnetic field and dl would have same direction. So for every portion you can write B dot dl is B dl cos 0. Take B out. Okay, you can take B out. This thing would become this, which is equal to mu naught capital N I. Why? Because all the turns are taking current inward. So current I is going inward n times. Same current is going first time, then comes out second time, third time, fourth time. So n times same current is going in. Is it okay? So Ni, and this thing would become 2 pi r. So B would be this 2 pi r mu naught Ni, B equal to mu naught which is actually very easily understood if you consider that we had a solenoid, we just rolled its end and joined them. We just turned the corners and joined. So a solenoid would form a toroid. How would the magnetic field change? It won't change at all. Okay, initially the solenoid was carrying same amount of field. Now when you turn it to form a toroid, it would carry the same amount of field. So everything is same. Solenoid has open ends, that's the only difference, right? So magnetic field has two places to come out, and in a toroid and there is no place to come out, for a tightly wound only, obviously. Is it okay? So now after all this grueling Ampere's law discussion, let's have one grueling question as well. Okay. Now we have this spiral. Okay. Carrying current I. The straight portions have no magnetic field. Is it okay? The straight portions have no magnetic field. Now the spiral has n turns and the inner radius is A, the outermost radius is B. The spiral has n turns, it carries a current I. What would be the magnetic field at center? Okay, this is the question. How would you approach it? You can well understand this, that actually it is not, it cannot be solved using what? Ampere's law. No symmetry, right? How to approach it? The width of this spiral would be how much? B minus A? है ना? It is tightly wound. I should write tightly wound so that you should get the idea that actually they are spiraled like this very tightly. The wires are spiraled like this very tightly. Okay. So width would be how much? B minus A. So number of turns per unit width कितना होगा? Number of turns per unit width would be how much? N by B minus A. In this much width, all the turns are covered. As you go away along radial direction, you need to cover this much distance, B minus A, radial distance B minus A, and you would cover all the turns. So which means turns per unit width would be this much. Okay. Why am I doing this? Because I would consider a thin strip somewhere like this. I would consider a thin strip of radius x but thickness dx. Radius x but thickness dx. Consider a thin strip of radius x and thickness dx. Okay. Okay. So number of turns for this, number of turns in width dx would be how much? dn is how much? कितने number of turns होंगे? In one width you had these many number of turns. In dx width you would have these many turns. This was for one width, right? For dx width, these many turns. Now since this is a strip, it is in the form of a circular ring or a coil. So you can calculate the field at center due to this coil. Okay. Field due to this circular strip at center, dB is how much? Mu naught, number of turns is dn, current is I through each turn upon 2x. For a circular coil it is mu naught I upon 2x, 2r, and when we have n number of turns, mu naught ni upon 2r. So you have mu naught I n by b minus a into dx by x. 2 also here. You getting the idea? Okay. What we would be doing? We would be integrating, and the limit would be how much? The minimum value of x can be a. Minimum radius is a, maximum is b. So minimum value is a, maximum is b. Mu naught I n upon 2 b minus a ln x होता and limits हम put कर रहे होते a to b, so this would be ln b minus ln a, right? So can we directly write it as ln b by a? Can we write this directly as ln b by a? Is it okay? Now this was asked in 2011 JE. Okay, this was asked in 2011 JE, and this was asked as an objective question, not subjective. Okay, the options were really close. Mu naught I upon 2b minus a, b minus a, ln b by a. Then in someone 2 was missing, in someone 4 was there, in someone some b minus a ki jagah a minus b something was there. So very tiny differences. Only when you know the correct expression, then you would be able to solve this. It is actual JE. So okay. In your sheet today, I would include one question. Try to solve it. If you are unable to solve it, please ask the doubt. The question is like this. I am giving you a hint. I hope everyone noted this down. The question is like this. A thick wire is there, cylindrical wire, long, out of which some portion is cut. So this is what? A cylindrical cavity. So all this portion is carrying a current, but only this portion is not carrying a current. So you need to find the field at this point, some outside point. Okay, what you would do is you would find the field because of whole of the cylinder. Then you would find the field due to smaller cylinder and you would subtract. We have already done this in electrostatics. Okay, we have already done this in electrostatics. Same kind of scenario exists in gravitation and all. Everywhere what happens? It is a application of superposition principle. Okay, complete the body, find the field, then take the cavity only, find the field and subtract. Is it okay? So I would be including this. If you have any doubt in this, please ask in the next class. I'll erase this. Now the easier portion comes. Okay. So out of this class, I think you would have a lot to take home, right? Only wire, loop, solenoid, toroid, okay, were known. Sheet was known. Then only these 4 were known to you actually. Rest all is new. Okay. Okay, and rest all was always at some point of time a part of JE. Rest all portions were a part of JE. Maybe some other portion, some 1 or 2 portions are left out. Maybe 1 or 2 derivations were not asked, but almost all of them were asked year after year in JE. Some were asked earlier, some were asked these days. Okay, so 2011 is not that much back, it's just 5 years back. Is it okay? So now let's start with the easier portion, that is force now. Okay, one portion, when one huge portion is finished, that is magnetic field. So let's start with magnetic field. We will discuss electromagnetic interactions first. Okay, first case, charge at rest. What happens when a charge is at rest? It produces electric field everywhere, है ना? It produces electric field everywhere, and it is attracted or repelled only by electric field. Only electric force acts. Only E vector produced and only electric force acts. What if a charge is moving when a charge is moving with velocity not equal to 0, okay, so it would produce electric field as well as magnetic field. Is it okay? So both electric field and magnetic field produced, okay, and both electric and magnetic force can act on charge. Okay. Now the third case, wire carrying current. What if we have a wire carrying current? Okay. In this scenario, the charges are moving, right? You already know that magnetic field is produced. Would electric field be produced? The charges are moving. There no electric field, only magnetic field. Why? The charge, the current carrying wire is neutral. A current carrying wire is always neutral, right? A current carrying wire is always neutral, so only B vector produced. Do you remember that only unbalanced charges produce electric field, right, or electric flux? The charges positive, negative are present at the same position, so they would produce equal and opposite electric field. So net electric field would be 0 everywhere, at any point of time, right? So only magnetic field produced. Why? Because wire is neutral. Whenever a wire carries current, it never gets charged. You know it, right? Whatever the amount of electrons are pumped into it, the other side of battery takes those many electrons out. Is it okay? If 10 electrons are pumped into the wire, the other end will lose 10 electrons. Hamesha neutral rehta, right? So wire is neutral, only magnetic field produced, and only magnetic force will act on wire. Okay, even though it has moving charges, even though it involves moving charges, only magnetic force would be produced, right? Okay, so can we move further? Now, just a second. So, magnetic force, let's find the magnetic force on moving charge. Okay, this you already would be knowing. Okay, let's say a charge Q is moving with some velocity V in a region of magnetic field where the angle between the two is theta. We can write the magnetic force as Q V cross B. The direction would be perpendicular to both V and B. So how to find the direction? Okay, just right hand thumb rule. Place your fingers along V, then curl them towards B. So the direction would be inwards. We would learn one more direction in some point of in some time. Okay, so direction inward. Direction right now is given by right hand thumb rule. If electric force is electric field is also present, let's say electric field is also present, okay, at some random direction, electric field is also present, then electric force would be QE. The total force acting on the charge would be how much? Q E vector plus V cross B vector. Okay, okay. The total force due to electric or magnetic field, this force is called Lorentz force. Okay, so when Lorentz force is acting, we can take components, portions. One is called Lorentz magnetic force, Lorentz electric force, The other one would be called Lorentz magnetic force, right? When both are acting, right? So let's continue. Where's the duster? Okay. Acha, you know that this can be written as QVB sine theta. QVB sine theta. I can obviously write it as QV sine theta into B. What is V sine theta in this case? V cos theta would be this thing. Component of velocity parallel to magnetic field. V sine theta is, this is V perpendicular, okay, and this is V parallel, right? So I can always write it as QV perpendicular B. So if you take only the perpendicular component, the direction can be given by another rule which is called Fleming left hand rule. Okay, if you consider only the perpendicular component. Why? Because the parallel component will give a cross product 0, right? The parallel component will give a cross product 0, so no force acts because of the parallel component, no magnetic force acts because of the parallel component, only perpendicular component plays the role. So if you are at the start itself taking only the perpendicular component, so there is another rule which is Fleming left hand rule, and left hand you know already, you have to stretch the fingers out like this, okay. So how to remember? This is, the thumb is for force, this is for magnetic field, this is for current or charge, the direction of motion of charge, okay. This left hand rule is applicable for positive charges. So if you have an electron moving, just apply this rule and take the direction opposite, okay. So if you have electron moving in this direction, the force on positive charge would be upward, electron would experience a force downward. How to remember this? You have very simple notation: father, mother, child. Father for force, mother for magnetic field, and child for charge. Okay, father, mother, child, it is applicable to both the cases, right? Is it okay? But this works when you take only the perpendicular component. You know, all these are perpendicular. The fingers, the thumb, they are perpendicular to each other, right? Okay, so I'll erase this one. Now, the first thing that we would study, we would first take the scenario in which the angle is 90 between the velocity and magnetic field. Then afterwards we would study cases in which the magnetic field and the angle between magnetic field and velocity is some acute angle or obtuse angle, okay. So let's first have this thing, work done by B, okay, work done by magnetic field. So let's say this is magnetic field, okay, a charge enters like this, okay. Since at any point F is perpendicular to V at any point, comma, for any angle theta, for any point and for any angle theta, force would be perpendicular to velocity, because cross product की property, okay. Why? Because F would be perpendicular to V and B both, cross product की property. So power would be F dot V is 0. Since power delivered at every point is 0, work done क्या, power क्या होती है? Rate of doing work. The rate of doing work is 0, right? Okay, you are not doing any work. Okay, so since power delivered at every point is 0, no work done, okay, for any portion, yeah, in any portion I should say, work done is also 0. You can anytime think it as f dot ds. Okay, if you try to find dw, which is f dot ds, again this ds would be along velocity, small amount of displacement would be along velocity, dot product would be 0 again every time. Okay, so magnetic field never does any work, whether the path is complete circle or half circle or whatever the portion may be, it would never do any work. So the time is over, and we would meet again after break.